All right, so we're looking at roots and zeros, and we're talking about the fundamental theorem of algebra, which obviously is a big kind of deal. Most of the stuff on this page we've talked about, but we're going to go over it again and talk about it one more time, okay? So the first thing I want to say before we look at that is, where are the solutions to that?
Where the line crosses the x-axis.
Okay, what do we call those things?
Zeros.
Zeros, what else?
Roots.
What is it?
Roots.
Roots, what else? Or what else could we call them? X-intercepts, and then also solutions, okay? All right, so we're still talking about the same thing. And, right, these are not just going to be parabolas. They're going to be different degrees, okay? So what they're saying right here, the first thing that they're saying is the zero of a function f of x is any value of c so that this happens. And so what are they saying there? F of x or f of c equals 0. What does that mean?
Whatever c is makes the equation equal to 0.
When you do what?
When you
plug it in. So when you plug this value into the function, you get a value of 0. Okay? And so then that means, because f of x stands for what?
The y.
Y. And so then what this is saying is there's some x value c that gives you a y value of 0, which means it's on the x-axis. Okay. All right, so then now they got a bunch of stuff here. And again, we just talked about this. But this is saying some function, and then all they're saying is it's in descending order, right? Biggest exponent first, followed by the next biggest, etc. So just some polynomial. And then we call a c could be a 0. It could be a root or a solution. And then they say x minus c is a factor. So notice the sign is opposite, and I'll show you about that here in a second. So again, all this stuff that we did before. And if c is a real number, then c comma 0 is the x-intercept on the graph. Okay, so now they give us an example. And so here's the function. I want to factor this right now. So what numbers multiply to give you negative 18 and add to give you positive 3?
6 and negative 3.
Oops, let me do this. There. So 6 and negative 3. So is it okay that this is what this factors into?
Yes.
Okay, and so then if I wanted to solve this, what would I have to do with those factors?
Plug them in. You'd have to.
So let me back up. Yeah, you would have to what?
Distribute.
No, I want to solve this equation. Like if I was asking, like, because wouldn't we do this? We'd say set equal to 0.
Yeah.
And so then what would you do to solve it?
Get x on the side by 2.
Because what do you do with those factors? So what is it? No, because we'd be going back to the beginning.
Is it the thing where you do like x squared plus 6x minus 3x?
Yeah, so we just got it to there to factor. All right, so then let's back up for a second. We set this thing equal to 0 because what we're saying is p of x is our y value. We want to know what the x values are when y is 0 because that gives us our x-intercepts. Okay, that's what that means. So then once you factor it, you can set both of these equal to 0.
Oh, yes.
And that's what you're doing. That's what you're actually doing. What is the x value when y is 0? Well, it's negative 6 and positive 3. Is that okay? All right, so then let's see what they're saying. This is a concrete example now, right? The zeros of this are negative 6 and 3, right? That means that the roots are also negative 6 and 3. Right? That means that the factors are right opposite signs, right? Because we were up here before we set it equal to 0. Is that okay? That was the x minus c part. And then if we wanted to plot these would be the coordinates. Is that okay? It's all stuff that we already did. Okay, now they have this statement down here. Every polynomial equation with degree greater than 0 has at least one root in the set of complex numbers. Give me, because they say that the polynomial has to have a degree greater than 0. What would be a degree that is 0? What would it look like?
Just a normal coefficient.
So give me an example.
2x.
That has a degree of 1.
2 would just be like
2. All right, so then what would the graph, because this is what he said, what would that graph look like?
It would just be like straight or something.
So it'd be this. So if the degree is 0, there are no x-intercepts. But as soon as we get a variable in there, right, the line starts switching, we start getting curves, okay? So that's what they're saying there. So it says, every polynomial equation with degree greater than 0 has at least one root, one place it crosses the x-axis, kind of, or one 0 we could find, okay? Because it says in the set of complex numbers. So what the heck's a complex number? What happens if we had a parabola that doesn't cross the x-axis? And we set that equation equal to 0 and use the quadratic formula.
The ugly eye.
You get the ugly eye. Okay, so complex numbers are a plus bi. Okay? So complex numbers are bigger than real numbers. Real numbers are all your integers, 1, 2, 3, 4, 5, and their negatives, 0, all the fractions, all the decimals, pi, square root of 2, etc. But none of those are i's. So complex numbers involve those plus anything with an I. Okay, so then again, every polynomial equation with degree greater than 0 has at least one root in the set of complex numbers, which means it might cross the x-axis, be a real number, or it may not and be a complex number. Okay, big deal. All right, this next thing I keep talking about, I don't know why we haven't talked about this yet, so I've already told you guys about this. And so instead of reading it, why are we saying that there are 3 roots here?
Because the degree is 3.
The degree is 3. Why are there 4 roots here?
Degree is 4.
Why are there 5 roots here?
Degree is 5.
Is that okay with everyone? All right, so we've already done that. Now, what I did say, though, is when we were solving these equations that you are looking for that many solutions, you may not get them, though. Okay, so that's what this next paragraph's about. So I'm going to do 2 examples. So they start off with, let's say that f of x equals x cubed. And I say to you, I want to find where it crosses the x-axis, and that's why I'm going to set y equal to 0. And so then if I solve that, what would you get as your answer? Well, first of all, how many should we be looking for? 3. But if I take the cube root of 0, what do I get? 0. So there's actually only one root. It's 0. But it counts as all 3 roots. So this is one root with a multiplicity of 3. Is that okay?
But it doesn't cross 0 3 times.
Correct. Okay, and I'm going to show you some shapes, and we're not going to get to this year, but you can look at a graph and certain shapes mean multiplicity happens. I'm going to show you what that looks like.
If it was 0 equals x squared, it would have a multiplicity of 2.
Right. Yeah, so if we just change this to, instead of x cubed, it would be x squared, you'd still just get 1, 0.
But it has multiplicity of 2.
Okay? And so if we do another one very similar to that, basically exactly what you said. So if I gave you this, I'm not going to ask you to factor this, I'm going to just do it for you. We could set that equal to 0 and it would factor into this. Now how many are we looking for? 2. But notice, right, that's supposed to be a plus. Notice that if we set them both equal to 0, they both give us -1. So then one root multiplicity of 2. Is that okay? Now again, we're not going to get to this, but it is something that's worth understanding. If I give you a graph like this, there's one value there, okay? If I give you this one, there's 2, okay? Now, the shape that a multiplicity of 2 looks like, let's do that one first, would be bouncing off. Counts twice, or 4 times, or 8 times, like an even amount. Bouncing off gives you multiplicities of even numbers.
So it would almost make like a V, like bouncing, or would it just?
It's going to be curved.
It's gonna be curved?
Yeah, because a V would be absolute value, and so that's still just 1. Okay, so that's a little bit different, yeah.
It gives you more than one root,
That would mean that there's an even amount there,
but it's the same number.
but it's the same number. An odd would do this little move. I think there is a name for this little move, but it would go like this. So it kind of acts like it's going to do something else, and then it keeps going. Okay? So that would be an odd amount of multiplicities. Now, that's just for information. That's not going to show up. It would show up sometime, but it's not really. I just want you guys to be aware that you can look at them and know these things. Because maybe you have it on Desmos, I don't know. All right, so that's a whole bunch of information. So is there any question about anything right now? Basically all the stuff we've already done. All right, flip the page in. All right, I'm not going to talk about Descartes yet. We're going to do example 1 first. And then we're going to come back to Descartes' rule of signs. So, example 1. Determine the number and type of the roots. Okay, so we have this polynomial set equal to 0. How many roots should we be looking for? 4. So once it's set equal to 0, if you can factor out something like we did here, x squared, then you can set the factors equal to 0. So then we're going to set x squared equal to 0. Is that showing up? Let me go back to light. And then x squared plus 49 equals to 0. And so then Jeff just mentioned this. We're going to take a square root of 0, and so then it's 0. But we were supposed to be looking for 2.
So this will have the
Multiplicity of 2. So that one counts for 2 of the ones you're looking for.
Is there a way that you show that has multiplicity of 2?
So
Like
you don't.
special sign or something?
No. So you don't. As far as you don't have to show that. You just have to understand. Like, I don't need to find another one. Like, I found that one counts twice, so I got 2 of mine taken care of so far. All right. So then on this one, right, we subtract 49 over. Take the square root. When you take a square root, you get a positive and negative. There's your 2 answers. Square root of a negative is I. Square root of 49 is 7, so that's why it's positive and negative 7i. So then there's the other 2. So that now we have accounted for 4. Okay, so then basically they've said all this, right? There's your multiplicity of 2. Call it a double root. Sweet. So it has 1 real repeated root at 0, 2 imaginary roots, negative 7i, and 7i. Is that okay? I know I'm hustling because I want to get through this for you. Because what time are we? 12:06. 06? Okay, we got plenty of time. All right, so now I'm going to jump up to Descartes, and I'm going to paraphrase Descartes' rule of signs, okay? So there's this French mathematician, René Descartes. He's actually like a really big deal because he's both one of the most famous philosophers and a very famous mathematician. And so this guy sat around and tried to find zeros of polynomials because we are just like they were 300 years ago. This guy's like in the late 1700s or something. We just got more junk, right? Like they were the same kind of people. They still had the same problems. They still wanted to go up in the air. They still wanted to shoot things and stuff. Okay, so they still needed to find these situations out. Now, you actually, or at least some people, I almost can guarantee, know something about René Descartes because he has the most famous philosophical quote of all time. So I think someone in here will know this. Have you ever heard, I think, therefore I am? That's René Descartes. He said that, okay? So, well, so not everyone's heard of it, but it's like it's a big deal, right? How do you know that you exist? I don't know that you actually exist. I know that I exist. I think, therefore I am. So I only know that I exist. So that's like the part of it.
You're not real.
It's the Matrix.
Yeah. Okay.
Simulation.
So anyway, he figured this thing out. So again, there's these ways. We don't have graphing calculators, so we got to find these roots. And you're blind. Like, right? Can you imagine how long it would take to hand plot this function? X to the fifth, like all that stuff, right? You plug in 1, you get a value. You plug in 2, you get a value. You plug in 3, you get a value. And so you can make this nice curved line, right? It would take a long time, right? Where does it cross a 0? It's hard to say. Okay, so then they started looking at different things that showed up. And so now I'm going to paraphrase what's going on up here. Okay? All you got to do, the first thing we're going to do is look at how many possible positive roots we have. And we're going to do that by counting the sign changes in the polynomial. And then we're going to do a little bit more than that, okay? So, but like, let's just look at this. And here's how it works. You never start with 1, but it goes from positive to negative. So there's 1. Negative. Now it's positive again, there's 2. Now it's negative, there's 3. Now there's positive, there's 4. So at most, because this guy made this theorem, right? He went through and proved it. We have at most 4 positive roots. Positive real roots. But there's a little bit more to that. So the first thing is because f of x, let's read through this. Because f of x has a degree of 5, it has 5 zeros, either real or imaginary. So there are 4 sign changes. Are we okay with that? 4 sign changes? Okay, now notice we have 3 blanks, so this is how it works. However many sign changes you have, that's the most it could be, 4. Then you start subtracting by 2. So then there could be 4 positive real roots, or 2 positive real roots, or maybe there are no positive real roots. That's our options. It's going to be one of those 3 things. All right, count your sign changes, start subtracting by 2, never go below 0. So if you stop at 1, then you're done. That's it. Is that okay? All right, we just talked about how many possible positive real zeros we have. So to figure out how many possible negative roots we have, we're going to do the same thing, except we have to evaluate the function at negative x. Now that means you're plugging in negative x every time you see an x, but it's a very simple move. Because a negative times a negative is what?
Positive.
Times a negative is?
Negative.
Times a positive is? Positive. All right, what did I say? I might have messed up. I messed up. Sorry.
Negative.
Did I say? Yeah, sorry. So, okay, so negative times a negative, positive, times a negative,
Positive.
negative, times a negative,
Positive.
times a negative,
Negative.
times a negative.
Positive.
Okay, so then every even root becomes, so a negative evaluated at a positive, I'm messing up, sorry. A negative evaluated at an even exponent is always, so like if you square a negative, it becomes, so no, it becomes positive. Right? A negative squared is positive.
Yeah.
So all even roots would be positive.
Okay.
Now for us, that means even roots don't change their sign. All odd exponents flip their sign. Okay, so here's what I'm saying. I'm going to do it right here so we can see it. So we have to evaluate it at negative. So a negative to the 5th is negative. So then this one becomes negative x to the 5th.
Oh, okay.
Okay.
Because that one's to the 4th. It was positive.
All right, but then that means it stays the same. So we don't change anything. It's not that it always becomes negative, it just doesn't change the sign. Okay? So an odd power changes sign, even power stays the same. All right, so then it's going to be plus x cubed
And then
plus 6x squared because it doesn't change,
Plus 5x.
5x.
plus because it does change, and then
Well, there's nothing.
there's nothing to change it, so then it'll do that. Is that okay? We'll do another one to get, but right? Now all we're doing is counting sign changes again. So how many sign changes on this one?
1.
1, is that okay?
Yeah.
So since there is only one sign change, there is one negative real 0, because you don't go, you should go down by 2, but you can't go below 0. Is that okay?
Yeah.
All right. So now let's go.
Have fun. Wish you luck. Safe journey.
All right, so we're still referring to the one on the other page. And so we need a total of 5 zeros. Why?
It's not degree.
X to the fifth, right? The biggest exponent is 5. Okay, so now one of our options was that we might have 4 positive ones. We're guaranteed to have one negative one. So if we have 4 positives, we have to have one negative. That would mean there are 0 imaginary because we have to add up to 5. The next option was that we had 2 positives. We had to have one negative, and then we needed 5 total, so that's where we get the 2 imaginary. So then if our third option on positives was 0, we had to have one negative,
And then there was 4 imaginary.
so that means there has to be 4 imaginary. Imaginary roots come in pairs. Is that okay? We're going to do it again. All right. All we're doing, we're going to make this chart. We're going to fill out this whole thing. It all has a place. So we're doing the positive ones first. So how many sign changes, bless you, how many sign changes happened with this original? 4. It should be 4. 4 sign changes. So then what are our possibilities for positive roots?
4, 2, and 0.
Okay, is that okay with everyone? All right. Now we're going to evaluate it at negative x. Does the first one change signs from the original?
Wait. No.
Yes.
No, because it's
It's an even.
an even. So then we're just going to write that one down. The next one's an odd, so is that okay? It just changes. Does the next one change? No. Does the next one change? Yes. Does the next one change? No. Does the next one change? Yes. And then that one without a variable doesn't ever change. Is that okay? And now you're just counting sign changes. So how many sign changes do we have on this one? 2. So what are our possibilities for 2 and 0? Now, does everyone understand why there's 2 and 0 there? Okay, so now we have all these like combinations that we got to work through because we still want to find out how many imaginary numbers we could be looking for. So, if I start off and say there's 4 positive reals,
There has to be
there might be 2 negatives. So then how many imaginaries would there be?
0.
0. Is that okay? But that wasn't our only option with negatives. So we could still have 4 positives.
The 0 negatives.
Then that would mean 0 negatives, 2 imaginary. Now we're going to jump down to the options when there's 2 positives. So 2 positive, 2 positive.
And so two negatives
it-
and two imaginary.
It could be 2 negatives, which means there would be 2 imaginary. Or if there's 2 positives, there could be,
0 negatives,
which means 4 imaginary. Is that okay? We're just counting. Okay, or we could have no positives, 2 negatives, 4 imaginary. Or no positives,
no negatives,
no negatives,
6
6 imaginaries. Because if you know your shapes real well, it's a 6. A 6 is something like this. So maybe it doesn't ever cross. Okay? Or maybe it crosses all over the place, right? Okay. Or maybe, on a 2, it could be like this. All right, is that okay?